Okay, so like ketones and aldehydes, the esters, the amides, the acyl chlorides, the anhydrides can undergo nucleophilic substitution. Okay, so they can undergo nucleophilic substitution. Remember, the aldehydes and ketones were doing nucleophilic addition. Okay, so the comparison here is both of them can be attacked by a nucleophile. That's why we call nucleophilic. But the derivatives, acid derivatives, do substitution while ketones did addition. What do I mean by that? So remember, let's say you had a ketone or you had an aldehyde. Okay, so whenever you reacted it with a nucleophile, it could be a Grignard, it could be OH minus. Okay, you attacked and this opened up. Okay, so that's an addition because you're adding the nucleophile. Okay, you're adding the nucleophile onto the carbonyl. But with carboxylic acid derivatives, something will leave, so it's gonna be substituted. Okay, so now generally we used to attack. This opens up, you get negative charge, and then you quench your negative charge by adding a proton and acid onto it. That's what we were doing. This part shows you the nucleophilic addition which happened in aldehydes and ketones. But for this chapter, we're going to be doing substitution because there's going to be a leaving group. When the nucleophile attacks the carbonyl of, let's say, an ester or an acid chloride, the chloride, if the chloride is here, the chloride is going to leave later on. So once you nucleophile attacks, carbonyl opens up, the lone pair of the oxygen is going to come back to make back the double bond. Okay, and because carbon cannot have 5 bonds around it once the double bond is reformed, the leaving group has to go. Okay, so, and that's characteristic of nucleophilic substitution. Okay, and that's what acid derivatives do. Okay, that's what carboxylic acid and its derivatives will do. The ketones and aldehydes will not do that. So I want to point something very important. You're starting with an sp2 carbon. You're going through an sp3 carbon, which means you're making a tetrahedral center intermediate. And then you're going back to sp2 carbon, which is going to be planar. So it started out planar, ends up planar, going through an intermediate which is tetrahedral. So these are the derivatives we should be considering. Okay, so assuming this one is substituted eventually, then that will be the leaving group, leaving us NH2 minus. See, the leaving group. If this is substituted, the leaving group will be OR minus. If this is substituted, the leaving group will be the carboxylate. If this branch or the side is substituted, the leaving group will be Cl minus once it falls off. Which of these one is the best leaving group? Obviously, chloride is the best leaving group because it's electronegative. Remember the rules for leaving groups. You want the leaving group to be a weak base after it leaves. So chloride is the weakest base of all these leaving groups from these derivatives, which means the weakest base. Okay, so it's the best leaving group. So increasing reactivity, the acid chloride will be the most reactive. Acid chloride will be the most reactive. because it has the weakest base, which happens to be the best leaving group. Okay, so the reactivity is based on the ability of the leaving group to leave as a key point. Nitrogen and oxygen, both of them have negative charge for these two, but nitrogen is the least electronegative out of the set. Least electronegative, which means it's the strongest. This leaving group here, NH2- is the strongest base. If it's the strongest base, then it's the poorest leaving group. So amides are the least reactive. Amides are the least reactive of the carboxylic acid derivatives. Remember, these guys can be made from the carboxylic acid, so that's why they are called carboxylic acid derivatives. If I was to place the carboxylic acid, it would have been somewhere between the amide and the ester. Okay, because OH- is a weaker base than NH2- if this had to leave. Okay, so this is an alkoxide. Alkoxides are strong bases, we use those for E2. And then this oxygen here is negatively charged, yes, but the leaving group is resonance stabilized. So anhydrides, this is called an anhydride derivative. This was an ester. Anhydrides are more reactive than regular esters, which don't have two carbonyls. And then the acid chloride will be the most reactive. So increasing stability means which one is not likely to react. So amide is not likely to react, so it's the most stable. Okay, most stable, not likely to react. Least stable will be acid chloride. Acid chloride, which means it's likely to react. Okay, so that's how these arrows, that's what those arrows mean. So like I said, the carboxylic acid has this structure. So if you replace the OH with NH2, or rather NR2, you get an amide. Okay, that's how you get an amide. If you replace the OH with the Cl, you get also chloride. If you replace the OH with an OR group, you get an ester. Okay, you get an ester. If you replace the OH with another ester, you get an anhydride. So let's say this let's say this OH, okay, is replaced by another ester looking functional group. Okay, or it's replaced by a carboxylate, so to speak. So you get an anhydride. You see, if you cut here, it's an ester. If you cut here, it's an ester. So it's anhydrides are mixed esters. They are diesters. Okay, so I've described how you get the amide. Just replace the OH with an NH2 or NR2, where R is carbon containing substituent. Okay. Esters. So you know these have a sweet smell. When your bananas are ripe, they are full of esters, and those esters will give it a sweet smell. Okay. So the OH of a carboxylic acid has been replaced by an OR group. That's how you get an ester. And this happens in nature, in enzymes, in digestive system, in your digestive tract, in your muscles. This reaction happens a lot in nature. Okay, in sugars, in proteins, name it. Creation of an ester happens a lot. All you need is an acid and an alcohol, and the presence of a little bit of an acid, you're gonna get an ester. So the OH and H will be lost from the carboxylic acid and the alcohol. So guess what you're forming? You're forming H2O. The H from the alcohol is gone. The HO from the carboxylic acid is gone. That's H2O. So it's a condensation reaction. And we're going to look at it right now. Going through a tetrahedral intermediate. You know, to condense is to bring together. So, and that's how you make an ester. You need an alcohol part or a carboxide part and a carboxyl part to make the ester as you lose water. This red part just means that's where you have much electron density, because of course those electrons, 2 lone pairs of electrons are there, and you can do resonances to push towards them, so the electron density is much on the carbonyl oxygen. We know we have another oxygen, but the carbonyl oxygen will have high electron density. Okay, so like I said, you prepare esters by a condensation reaction. And there's a scientist who discovered this reaction is called Fischer. So we're making ester, so it's Fischer esterification. So you have to have the carboxylic part and you have to have the alcohol part. So like I told you, the shortcut is very simple. Okay, realign your molecule to where you can circle the water that's going to be lost. That will be lost as water, which is that. And then click the 2 parts together. So this is your OR group. That's the shortcut. Okay, that's a general shortcut to predicting the products. But you do need acid catalyst because carboxylic acids are not as reactive. Okay, you need an acid catalyst to drive the reaction forward. And in the lab, we usually find a way to take out this water according to Le Chatelier's principle, which states that when a reaction is subjected to a change, it will counteract to counteract the change, to oppose the change. So if you're taking out products, you make more products to avoid it to be much of an equilibrium reaction, so the reaction keep going forward. Okay, so to drive it forward, you either use excess alcohol acid or take off the ester or take off the water as it formed. The easiest here to do is to take out the water. We usually use what we call a U-tube, a glassware that has a U shape. As the reaction goes forward, the water droplets collect outside the setup in a U-tube. So the reaction will keep going forward. So let's look at Fischer esterification mechanism. Okay, so the Fischer esterification mechanism. So like we say, the carboxylic acid carbonyl is not reactive. So we need the acid catalyst. We use the lone pair to activate it. Only then will the alcohol come in. Use the lone pair on the oxygen. So the alcohol play the role of a nucleophile. The activated carboxylic acid will play the role of an electrophile. Okay, remember, electrophile receive electrons, nucleophile donate the electrons. So the nucleophile is attacking the partially positive carbon. It's now very activated because now the oxygen is bearing a plus charge. You can imagine how strong the dipole moments will be. So the alcohol is attacking the activated carbonyl, and then you neutralize the plus charge. So notice that O plus H becomes OH. The plus charge is neutralized. And then because the alcohol used its lone pair, it's left with 1 lone pair. You'll have a plus charge on it, on the oxygen. Like I always tell you, organic molecules don't like being charged. If there's a way they can get rid of the charge. Okay, so the water that was used to dilute this acid will be used to deprotonate. So this is deprotonation. It's deprotonation of the tetrahedral intermediate. Why do I call it tetrahedral? Because you started off with an sp2 carbonyl center, which of course is trigonal planar. You end up with sp3. After this addition step, you end up with sp3 tetrahedral molecular geometry. Okay, so this is your tetrahedral intermediate. Actually, that's your tetrahedral intermediate. This one's a tetrahedral intermediate. So this is the official tetrahedral intermediate because it's neutral. There's no charge on the structure. Okay, it's neutral. So once the water takes out this extra hydrogen, you neutralize the oxygen. The arrow should point in the oxygen. You had a plus charge on it. So you're gonna get H3O plus as a byproduct. When H2O gains another hydrogen, get H3O plus. But we don't need two OHs. So one of these OHs will be activated to leave because OH is a poor leaving group. If it leaves as OH minus, it makes a strong base. Good leaving groups must make weak bases. So we activate it by accepting a proton from the acid. You see how you form the H2O plus here is going to play the role of an acid. Acids are proton donors. Okay. Hydronium ion is an acid because we can use the lone pair to come and pick this up and neutralize the water. So allow me just to say H plus, okay, instead of pushing this arrow onto here. So let's just accept the H plus. Now, because the oxygen used its lone pair, it becomes positively charged. The positive charge is on oxygen, not on hydrogen. And now you can use the lone pair on the other oxygen to make a double bond, to make a pi bond, okay, in between the oxygen and the tetrahedral carbon center. At the same time, water leaves. That's what this subtraction means. Okay, doing so, you're left with one lone pair. You're left with one lone pair on the oxygen and a plus charge. Like I keep saying, okay, you know, this is lost. This part is lost as water. That's what this implies. I keep saying organic molecules don't like being charged. So the water that fell off, that was lost, is going to be used using the lone pair on the oxygen to deprotonate by proton transfer, which is the same step here, which was proton transfer. Okay. So deprotonation of this hydrogen by proton transfer helps you to neutralize the oxygen. Again, because the water took out the hydrogen, you get H3O plus. So that's the mechanism of making the ester. You realize now you have OR prime, which came from the alcohol. So simply put, if you have your carboxylic acid and your alcohol part, I'll keep telling you this shortcut is gonna save you in the test. Just know eventually you have to lose water. You see how water is lost? So the hydrogen of the alcohol and the OH of the carboxylic acid will be lost as, okay, lost as H2O. So the OR prime will be combined with the carboxylic acid part. You get an ester. Okay, so this molecule right here is just this molecule right here. So that's the general idea. This happens through all these messy mechanisms. Unfortunately, that's a language for organic chemistry. withdrawal mechanisms. Now, whenever you do acid catalyzed reactions, every step in the mechanism is reversible. So the entire reaction is reversible, unless, of course, you apply Le Chatelier's principle in your setup, where you keep on taking out all the products as they are formed, or one of the products like water as it's formed in esterification, as explained here. If you want to push the reaction forward, keep taking out the water as it formed. You're creating space on this side. The reaction will go mostly forward than backwards. You will be getting rid of the reversibility of each steps. Okay. The OR part comes from the alcohol, because the alcohol uses its oxygen to attack the carboxylate activated carbon of the carbonyl. And of course, we use radioisotopic labeling to do this. You know, the thing is this: if you start with a carboxylic acid, and you know the mass of oxygen should be 16, right? But oxygen has an isotope called oxygen 18. Isotopes are just elements having different mass numbers, because they have different number of neutrons. So, okay. So let's say our alcohol is oxygen 18, an isotope of oxygen 16. Using an instrument called mass spec, we can determine whether this oxygen was put there and the oxygen 16 fell off, or oxygen 16 was kept and oxygen 18 fell off. That's what's called radioisotopic labeling, because in this reaction it was found out that the oxygen 18 stayed. Okay, whenever this scientist called Fisher was doing the mechanistic studies, he discovered that during this reaction, the oxygen of the alcohol stays, the oxygen of the carboxylic acid goes. You no longer have the oxygen 16. Where did that go? It's lost as part of the water. Okay, it's lost as part of the water. So you see, if you do the formula mass of this, it's gonna be 2 units more than when you would have thought that you're keeping your oxygen 16 and the R prime group. This is 2 mass units less than that. So there's an instrument called mass spec that they used, and they found that actually the product in this experiment had 2 more mass units, and that meant that it's the oxygen of the alcohol that stayed, the oxygen of the carboxylic acid left. That's radioisotopic labeling. I'm just giving you an overview of how that worked to know who stayed, which oxygen stayed, which oxygen left. Just using isotopes of oxygen, you'll know. So this was not observed. Instead, this was observed. That proved the mechanism. That proved that this mechanism is right, that the oxygen of the alcohol is added, the oxygen of the carboxylic acid falls off. Alright. Again, note that we are doing substitution because you started with OH and you're going to substitute it with OR of the alcohol. Lactones are cyclic esters. So far we've just been looking at chain esters, right? But you can have a ring of whichever size that has an ester in it. As you can see, that's an ester group. So whenever the ester is within a ring, we call that product a lactone. Okay, and lactones are used in drugs. For example, some of the antibiotics, they work by opening up the lactone ring of an enzyme, or the lactone ring of the the antigens. So you learn those in biochemistry. You have to take biochemistry, how the drugs work. So it's important to know what lactones are. So commonly we have 5-membered ring, like this one here is a 5-membered ring, 1, 2, 3, 4, 5, or you can have a 6-membered ring like this one. It's a cyclic ester because I have a carbon here and a carbon here, so it's a lactone. And this can be made obviously by just using Fischer esterification. The only difference is that you have your carboxyl group and the alcohol on the same structure. So if you fold it, it's gonna make things easier. So let's say this is your carboxylic acid, right? And you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'm gonna put the alcohol right here, and I'm intentionally using the blue color because we say the oxygen of the alcohol stays, the oxygen of the OH leaves. So one can easily use our baby shortcut. We know that we can quickly know the product by losing the OH of the carboxylic acid and the H of the alcohol and clicking the oxygen to the carbonyl, because we know that oxygen stays of the alcohol, the OH of the carboxylic acid falls off, and that's how one would form water. So the OH of the carboxylic acid and the H of the alcohol will leave. This is H2O. Okay, so click the blue oxygen to the carbonyl, you get the product. Okay, and it happens to be an ester. It's a ring, so we call it a lactone. So the mechanism for making the lactone is very, very similar, but here I just showed you the exam survival shortcut. Okay. For those who are curious about the mechanism, it's very, very similar. It's still Fischer esterification, but in this case, the only difference is that you're gonna do cyclization, because that's how you'll make lactones, which are cyclic esters. So carbonyl of the acid is less reactive, so activate it by attacking a proton of an acid catalyst. Okay, so you'll be left with one lone pair. Oxygen will take a plus charge, and then use your alcohol, which is within the same structure, to attack the carbonyl, activated carbonyl of the acid. That will cause this pi bond to open up. Okay, that arrow is missing. Notice that each step is an equilibrium unless you keep taking out water. Can go back and forth. So the lactone can open up even after it's formed to go back to the open carboxylic acid alcohol moiety. So you attack the carbon, activated carbon of the carbon, it opens up, you get this structure. So for traction, this OH is going to be this OH, and this bond is this bond. The best thing you can do for yourself is to number the carbon so you know. So this is carbon 1, 2, 3, 4, 5, and 6. So it happens to be carbon 1. For the alcohol it's carbon 5, and then that's 6. So 1, 2, 3, 4, 5, 6. We are making a 6-member ring because oxygen is the 6th element of the ring. Like I always tell you, organic molecules don't like being charged where they can uncharge themselves. So the lone pair of one of the OHs, see, once you attack carbon 1, you're gonna get OH and OH. Those are these two OHs. The oxygen of one of the OHs will play the rubber base to deprotonate the oxygen of the 6-membered ring, and then use the bond to neutralize that positively charged oxygen. So you get this. And then now you can have a good leaving group, because these OHs, one of them cannot leave, because once it leaves as OH minus. It's a strong base. So we use the lone pair of the other OH to make a pi bond. As you do that, that causes a push effect. Water is lost. See, this guy is lost as water. You made your double bond. This oxygen has now one lone pair. You have to have a plus charge with it. Okay, and now we are fixing to get to lactone, which does not have any charges. So we use the water that fell off to neutralize this organic molecule, because again, organic molecules don't like being charged. So use the bond to neutralize the oxygen. You end up with your lactone. When the water accepts the extra hydrogen, you get H3O+. So that's the mechanism for making lactones. All right. Saponification. This is also called ester hydrolysis. Hydrolysis because you are using the elements of water to break down esters. But because you are using a strong base, we call it saponification. And it's also because this is the way we make soap. So saponification. You know, those taking organic 263, the lab for this class, you probably will do soap synthesis. Usually we use lard that comes from the pig's thigh. It's made of what we call a triglyceride, which is just one huge molecule with 3 ester groups. You chop the ester groups, you're gonna end up with what we call stearate, which is your soap. Okay. All right. So we can use a strong base. That's the best method. Some people use acids to do this, but bases help the reaction to go one way. The acid, like I said, we call reversible reaction. So we like using base as a reagent because the reaction is going to be reversible. If you use an acid, it's going to be reversible. Like we've seen here, you see going back is still ester hydrolysis. You'll be breaking your ester from this joint going back to get back to this point. That will be acid catalyzed, but it's reversible. So we prefer using, it's feasible, it's practical to use a base for this reaction. So what's happening here? It's some type of substitution. So you'll be carrying this point, the R group falls off as O minus, OR minus. I know it's a strong base, but because the reaction's base catalyzed, is bound to go. And then it's going to pick up a proton from water, you get back your alcohol. The acid part would become a carboxylate, which is called soap. Okay, so let's look keenly at the mechanism. Before that, we know that this is ionic, right? So that's why soap is highly soluble in water, because one can expect to form ion hydrogen bonding. Because this is negatively charged, the water molecule is positively charged. These two can bind. Then you get to dissolve your soap in the water when you're doing laundry. Okay, so let's look at the mechanism for saponification. So if you have this specific ester where the R group is an ET, you have your hydroxide which came from sodium hydroxide. It's just a spectator ion. There's a problem with the arrow. This is not an arrow on this side. So one would use one of the lone pairs on OH minus to attack the carbonyl. It opens up, you get again your tetrahedral intermediate that I emphasized when we started. It's tetrahedral because that carbon is sp3 now. It started off sp2. which is trigonoplanar. So now your OH of the base is added. Can you see it? It's right here. It's added. Carbonyl opened up. Now you get O minus because this oxygen now has 3 lone pairs. Okay. And now the lone pair, extra lone pair on oxygen can come back to create a carbonyl by making a pi bond as the OR group leaves. In this case, OET leaves. So you get OET minus. Now because the OET minus is a strong base, it's gonna come back and deprotonate the acid. You know, this is a carboxylic acid. That's a base. So the base will use its lone pair to deprotonate the carboxylic acid. You use this bond, donate the lone pair onto the oxygen. Now the oxygen has 3 lone pairs, so it's gonna be negatively charged. It gives you the carboxylate. You know, I told you before, carboxylic acids react with bases to give you carboxylates. Carboxylates are salts. They are ionic. They are water soluble because salts dissolve in water. Soluble. They are water soluble. Okay. Clean it up so you can read well. Water soluble. Now the alkoxide, in this case, the alkoxide is ethoxide. The ethoxide accepts the extra proton, so now you have an alcohol. Alright? So you will have moved from your ester all the way to your carboxylate. Okay, sorry about that. All the way to your carboxylate. This blue oxygen came from OH minus because that's the oxygen that attacked the carbonyl. So you broke apart your ester using elements of water. You know, OH minus is part of the structure of water. So it's called ester hydrolysis. And it's base catalyzed, so it's saponification. Saponification. And also you're making soap. That's why we call it saponification. It's not supposed to be reversible, especially the last step is not reversible. So we prefer using base catalysis rather than acid catalysis, which everywhere would have been reversible. Okay, so there's another reaction called ammonolysis. As you can tell from the name, you're gonna use ammonia to break down the esters, because lysis, as in biology, is just break up or break down. Okay, using ammonia this time. We are not using water. If it was water, we'll call it hydrolysis, but you're using ammonia. So just like OH minus did, here, ammonia can do it, although at a slower rate. So you can imagine attacking this carbonyl and then this falling off, and then OR minus takes out the extra hydrogen, you get an amide. So in these reactions where amines attacks esters, okay, esters attacked by amines, sorry, I think it's 1M. Esters attacked by amines is called ammonolysis. Alright, so let's look at the mechanism. The low pair of nitrogen attacks the carbonyl of the ester. Carbonyl opens up. You started again with sp2, which is trigonoplanar. You end up with sp3, which is tetrahedral. That's a tetrahedral intermediate. Okay. Yeah. And now, since nitrogen is comfortable with 3 bonds, now it has 4 bonds. You know, if you draw this structure, you realize that the nitrogen now is bound to 4 bonds, the 3 hydrogens and the carbon. So the nitrogen will have a plus charge. So one can lose it by creating your pi bond back. So let me get rid of that line so you can clearly see. So you use the O minus oxygen to create a pi bond back. The OR groups falls off. In this case is OCH3. Okay. OCH3. So you just made this. You just made this structure. Now this is the OCH3 that fell off. In fact, let me just draw it here for clarity. So you made your carbonyl, and then you have your NH3 plus, right? And then the alkoxide fell off as OCH3. You know, alkoxides again are strong bases, right? So what do you think should happen? This is a strong base. The nitrogen is positively charged, so the strong base will be used to deprotonate or to do proton transfer to neutralize the nitrogen. From that step, you're gonna get your amide, and that's what's happening here. I don't like the way the arrow is shown here. I think it's a software issue, but in open bond drawing, that's exactly what's happening. You make your double bond, the OCH3 falls off. It's a strong base, so it's going to be used to deprotonate or neutralize this organic molecule, because organic molecules don't like to be positively charged. So the O negative CH3 now is transformed to OCH3H, which happens to be methanol. So you will have transformed your methoxide to methanol. At the same time, you will have transformed your ester to an amide. And that reaction is called ammonolysis. Okay. Now, let me give you the shortcut again for this one, because I like giving shortcuts where it's possible. So you see how you have OCH3 and you have ammonia. So we're going to use the same trick. Okay. So I'm going to show one of the hydrogens from the amine. Okay, I know that the nitrogen should end up attached on the carbonyl, so this part must go. So in our case, it goes as methanol, right? Because we want to click the NH2 to the carbonyl, and that's what's happening here. So when that happens, you get your NH2 bound to your carbonyl. Okay, so this is how you quickly predict products without going through the mechanism. Okay, that happens to be your amide. Okay, the bond formed is called an amide bond. And then, of course, what's lost? The red OR group, OCH3 group, and the hydrogen part of ammonia. And that's the methanol. Okay, which is this part. So you can still use a similar shortcut like we did for esters, where the OH and the H of the alcohol are lost to get water. Now here we lose an alcohol instead of water. Okay, now how do esters react with Grignards? They're gonna need two equivalents to produce the final alcohol. The reason is one has to go through a ketone, and the ketone still can react with the second equivalent of a Grignard to give you the alkoxide, which is protonated to give you the alcohol. Let's go through the mechanism to justify why we need a Grignard in two equivalents, why we need excess of Grignard. So remember what I said about Grignard reagents. If you have a carbon and a metal, assume that you just break this bond and make that immediate carbon negatively charged. Magnesium bromide just becomes a counter spectator ion. So we can start pushing from this bond, or we can, if we look at it this way, we can still do The same thing here. Okay, so you're adding your isopropyl onto the carbonyl of the ester. The pi bond of the carbonyl opens up. You started off with an sp2 carbon right there. Now it's sp3. So again, you're going through the key tetrahedral intermediate that I keep emphasizing. Okay, let's clean up. So you end up with a tetrahedral intermediate. Of which the lone pair of oxygen can come back to make a double bond. Because Grignards are in the presence of a very strong base environment. Grignards are strong bases, strong nucleophiles. So all R groups can leave as OET even though it's a strong base, but the Grignard itself is a stronger base than OET minus. So you make a double bond, a pi bond, the OET leaves, not the R group, it's the OET leaves, because oxygen is more electronegative than the carbon, so it's the R group that leaves, not the carbon. So you make your pi bond again, like I said, which creates the carbonyl, which happens to be a ketone because you have CC carbonyl. Next, so this was the first equivalent, okay? Next is the second equivalent. So for the second equivalent of Grignard, you do the same thing. Start the arrow from the bond of the Grignard or start from the carbanion, whichever way. You're adding the second isopropyl group. You attack the carbonyl, this opens up. Notice that now you've ended up with two isopropyl groups, or two R groups are added. Again, it's a tetrahedral intermediate, just like we had up there. This is a tetrahedral intermediate. Do you think we can form the carbonyl back? No, because there's no leaving group. So instead, we just end the reaction by protonating the oxygen, because organic molecules don't like being charged. You end up with a tertiary alcohol. So if this was one equivalent, this is where you'll stop. But that rarely happens. So we'll just rather use two equivalents of Grignards, go stepwise, and add the R group of the Grignard twice. You end up with a tertiary alcohol. It's tertiary alcohol because the carbon bearing the OH is bonded to three other carbons, so it's tertiary. That's an R group, that's an R group, that's an R group. Okay, so the second addition occurs since the ketone is still reactive to Grignard. We all know that ketones can do Grignard reaction. Okay, to give you a tertiary alcohol. Of course, once you quench step 1, if you do the addition of the Grignard, step 2, if you quench with an acid, you're going to end up with a tertiary alcohol. This is a good method of making tertiary alcohols. So generally we started with an ester, which gave us, after the first Grignard, it gave us a ketone. The ketone is still reactive to Grignard. It gives us the tertiary alcohol after the second addition. So that's why we needed two equivalents. Okay, 2 mole equivalents of Grignard. So you add twice to make the alcohol. Okay. Esters can be reduced by hydrides. Remember what we said in carbonyl containing compounds, the ketones and the aldehydes, that if you use hydrides, you can add the hydrogens across. Now, lithium aluminium hydride has 4 hydrides to give. So, if you react the ester here with lithium aluminium hydride, this does not work with sodium borohydride. It has to be a strong reducing agent like lithium aluminium hydride. Sodium borohydride don't react with esters. Okay, it does not reduce esters to alcohols. In fact, the reaction does not just happen, it never happens. So now let's say we are adding the first hydride from lithium aluminium hydride. It's a substitution reaction because this will attack that and this falls off generally. speaking. I'm not showing the full mechanism. So one would end up with that. And what's that structure? What functional group is that? It's an aldehyde. Okay, you know aldehydes are more reactive than even ketones. So because we have extra hydrides to give, there are 4 of them, one can bring another hydride from lithium aluminum hydride. Okay, this comes from lithium aluminum hydride, because there are 4 that can be given. So do the same thing. This time there's no leaving group. Here there was a leaving group. Here there's no leaving group. So if you do that addition, in summary you get O minus. Okay, and then that's the brown hydride that you just added, and this was the first hydrogen that you added. And of course one can imagine that if the O minus is quenched by an acid, which is this step, which just provides an acid, then you're gonna end up with an alcohol with your 2 hydrogens. Now what type of alcohol is that? The C bearing the OH is bonded to 1R group, so this is primary alcohol. And that's what this says. This says the product is a primary alcohol. After you reduce the ester with lithium aluminum hydride, you end up with primary alcohol. So generally you're starting with your ester, which goes all the way. This carbon is still there, but it's gonna accept 2 hydrogens. Remember what we said reduction is? Reduction is addition of hydrogens or removal of oxygen. So here we are adding hydrogens. These 2 hydrogens were added in form of hydrides. Okay, so it's reduction. You get alcohol, and it's a primary alcohol made from the esters. So that was just the general summary of what happened here. Okay, so mechanistically, don't worry about that, just use the hydride, attack the carbonyl, you get your sp3 tetrahedral center. I'll keep telling you about the tetrahedral intermediate, very important. Okay, so the hydride attacked, the carbonyl is opened up, that's the hydride, and then OET fell off. When this comes back down, the OET falls off. This is CH2, CH3, which is the ET part. ET is just CH3, CH2, right? When you make back the carbonyl, the OET falls off, you get an aldehyde for this molecule. And then still you can use another hydride from lithium aluminum hydride to attack the carbonyl, because this aldehyde, which is just this aldehyde withdrawn, is reactive. Open it up, you add 2 hydrides, you get O minus, because the carbonyl opened up, which had 2 lone pairs, now you have 3 lone pairs, you get a negative formal charge. Quench with an acid, you get again primary alcohol. It's primary because you have 1 R group attached to the carbon bearing the OH. Now, the aldehyde cannot be isolated. This one cannot be isolated. Where's the aldehyde? This guy cannot be isolated. So the reaction simply goes through it, but you will never isolate it and stop. You can never stop the reaction halfway. Okay, it's still reactive, super reactive, so that's why the aldehyde will go further to be reduced to the final alcohol. Lithium aluminum hydride is selective for carbonyls, does not react with double bonds. So for example, if you have, let's say you have this ester, okay, the double bond will survive. I have to redraw it so you can see it. The double bond will survive. The CC double bond will survive, but the double bond on the carbonyl will go. Okay, you end up with that because where the carbonyl was, you're gonna put 2 hydrogens. from the two hydrides, which are added stepwise. So the double bond survives, so lithium aluminium hydride is selective. Only reacts with the double bond of the carbonyl, but not the double bond of the alkene. Sodium borohydride, like I said, is mild. It does not reduce acid derivatives or carboxylic acid. So if you have a ketone, if you have an aldehyde and a ketone and an ester on the same molecule, and you're using sodium borohydride, guess who will react? Only the ketone and the aldehyde will be reduced. So the aldehyde will be reduced to primary alcohol on that part. The ketone will be reduced to a secondary alcohol, but the ester will stay. So that's an application of sodium borohydride. It allows for the selective reduction of aldehyde and ketones in the presence of esters. So let's summarize what we just talked about. So acid derivatives most likely will have leaving groups. So nucleophile attacks, you get a tetrahedral intermediate. Okay. Which after rearrangement and reformation of the carbonyl, okay, the leaving group leaves. So you get a carbonyl product which can end up to make an alcohol. Many of these reactions are reversible unless you're using a strong base. Okay. The rate is faster when the leaving group is more electron withdrawing or resonance stabilized. Okay, so the carbonyl structures can have resonance stabilization. In general, acids and esters are less reactive than aldehydes and ketones because this is ketones or aldehydes, but for the esters, there's a lone pair here that kills the plus character of the carbon, which deactivates that towards nucleophilic attack. Because the nucleophile wants the plus charge to be there, but the moment you do resonances, you're killing the plus charge. So the ester or carboxylic acid are less reactive than ketones because you see here there's no second oxygen to kill the plus character. So this is a case of ketones and aldehydes. So in other words, aldehydes and ketones are more reactive than esters because with esters the carbon of the carbon is deactivated by resonance. You're pushing electrons, killing the plus character on the carbonyl. So one would want to have something that pulls out electrons, which helps the plus chance to stay, and that is the case where we have acid chlorides. That's why acid chlorides are more reactive, because this carbon here is made super positive to be attacked by a nucleophile. Okay, and that's where we started. How can you make an acid ester more reactive? Simply do acid catalyzed reaction. That's one. Alternatively, substitute the OH of carboxylic acid to a good leaving group like Cl. That way the OH or the OR group will be more reactive. Okay, that's why I said iso halides are more reactive than esters and carbonyls because you have a good leaving group. Okay. They do not exist in nature. We usually make them in the lab so we can use them. Chloride is the most common acyl chloride because Cl is the most common leaving group here. And we will talk about the preparation next time.